So now we're opening up Rational Roots Theorem. And what this theorem is used for is the factoring of polynomials which have an order higher than 2, or the degree of the polynomial, this exponent right here, is higher than 2. The reason 2 is an important degree is because when you have a quadratic polynomial, x squared plus something, those are the sorts of things we can factor pretty easily using the techniques we've been over in the past, the big X, for example. But when you get to x cubed and x to the 4th and x to the 5th, it really gets difficult. So we have this rational roots theorem which helps us try to narrow down the possible factors of f of x. So, as we went over in class, this number right here we designate p. And this number over here, the leading coefficient, we designate q. And we're going to say that all the possible factors, all the possible roots for f of x are in this list. The factors of p divided by the factors of q. This isn't the actual roots. These are the possible roots. And remember, these are the possible rational roots. Remember, this is called the rational roots theorem. So if you have imaginary roots, this isn't going to help you. But this will track down the rational roots. And don't forget, it's a plus and minus. So let's use this example and figure out what we have here. Well, p is 12. So I want factors of 12 over factors of 4. So what is that? That's 1, 2, 3, 4, 6, and 12. 12 is kind of an obnoxious one. It has a lot of factors. But there's not too many factors of 4. It's just 1, 2, and 4. So let's make a list of all of these things, and I might need more room. We'll see. So I'm going to start going along the top first. I'm going to do the entire, let me do this in colors here. I'm going to do the entire top row and just the number 1 on the denominator. Okay, so that's where these are coming from. I have 1, 2, 3, 4, 6, and 12. All of those divided by 1 just turn into the same thing, so we don't need to write anything extra. Now I'm going to do this whole top row divided by 2. So we have 1/2. And we have 2 halves, but think about 2 halves for a second. That's just equal to 1, and we already have 1 in our list. So you can cross that one out. And then we have 3 halves. 4 halves we already have in the list as the number 2. 6 halves, 12 halves, those are duplicates. So I can just stop with 1/2 and 3/2. And now we're going to move on to the fourths. So I have 1/4. 2/4, if you think about it, is already in our list. That's just 1/2. So I'm going to ignore 2/4 because it's a duplicate. And let's see, how about 6/4? Well, 6/4 is equal to 3 halves, so that's a duplicate. And 12/4 is equal to 3, so that's a duplicate. So I think I have all our, we missed one. Careful. We missed 3/4. Okay, so let's put 3/4 in the list. So those are all our possible rational roots, but don't forget, this was plus and minus. Some of these might be positive or negative, so I'm just going to stick a plus or minus right here. When you answer this in the computer, it probably wants you to write out +1, +2, +3, etc., -1, -2, -3, etc., because there's no plus or minus button that you have to select from. So that's going to be a little tedious, and that's just life with the rational roots theorem. Now we get on to finding the actual roots. So the actual roots for f of x is a subset of this big, long list of possibilities. We have to search that big list to find the actual roots. And you may be looking at this thinking like, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times plus and minus. So that's 20 possible roots. In other words, 20 possible versions of a synthetic theorem. No, thank you. Well, actually, it's not that bad because as soon as you find one root, things are going to get easier. So usually the key is just finding the first root. Oh, come on. What's going on here? So let's start the synthetic division. And I always like to start my synthetic division with the ones because it's easier, right? Where's my pen? Come here. We're going to start with the ones, and then we'll move to the twos and see how things are going. So, synthetic division. You start with a bar like this, and you put your coefficients up top, 4, 13, 4, and -12, and you put the root that you're trying to find over here. So I'm going to start with +1 as the root. Now, you could go forward with synthetic division, and we'll get plenty of practice with this, but I just want to point out something. Remember the remainder theorem? I hope you remember how to use it, because there's a quick way you can avoid synthetic division if you know the remainder theorem, which is that the remainder, when you divide f of x minus, or divided by x minus 1, the remainder is f of 1. Now we want the remainder to be 0. If the remainder is 0, we found a factor. We found a real root. So does f of 1 equal 0? That's my question. Well, 1 cubed is just 1. 1 squared is just 1. 1, this should be pretty quick. Does 4 plus 13 plus 4 minus 12 equal 0? And I don't even have to do the math. I just know it's not equal to 0 because there's a lot of numbers over there that are bigger than 12. So it turns out we have a shortcut. We can sometimes use the remainder theorem to get out of checking all these numbers if you can just quickly plug it in and say, oh, well, that's definitely not going to be equal to 0. Okay, so I'm going to skip 1 for that reason, and let's move on to negative 1. I'm not so sure about negative 1. So 4, negative 1 times that makes negative 4, 9, negative 9, negative 5, positive 5, negative 7. That's not equal to 0. So negative 1 is not a root, which means, okay, we can cross that off our list, and we start over. Let's pick something else. I like to go with the whole numbers before I get into fractions. Getting into fractions is kind of scary. We'll get to it, but I try to avoid it. So if I plug in 2, remember that remainder trick? Look at this. 4 2 cubed. I don't know what that is off the top of my head, but it's big. And so is 13 2 squared, and so is 4 times 2. Well, 4 times 2 is just 8. But the point is, all of these first 3 things are adding up to more than 12. So I know that this is going to be not equal to 0, right? The remainder of this is not equal to 0, which means I don't need to check 2. I know it's not going to work. So we can move on to negative 2. So we have 4, negative 2 times that is negative 8. This becomes 5. Then we have negative 10. Then we have negative 6. Then we have 12. Oh, look at this. This is nice. Okay, we've got a remainder equal to 0. That means negative 2 is a root. So first thing I want to do is factor this equation now. F of x, instead of writing this whole big thing, we're going to factor it down with x plus 2 getting pulled out. That's the root we just found. X equals negative 2 times 4x squared plus 5x minus 6. Okay? So at this point, I would recommend you go forward and factor this part using the big X. Okay? It's much quicker that way. But I'm going to go through how I would continue to use synthetic division, because when you're looking at a 4th order polynomial or a 5th order polynomial, you'll need to do this a few times. So we just need to get in that habit. Now, the last root we found was negative 2. Okay, let's start our synthetic division over again. And this time, I'm taking the roots of this quotient right here, because I don't want to know if my next factor goes into the original. I want to know if my next factor goes into this part we have left over. That way we can continue to factor this down and down and down until it's just a bunch of linear terms. So I'm going to take these coefficients from my last answer, 4, 5, and negative 6, and plug those in as the top line. And what do we plug in here? Okay, think about that for a second. Which root do we check next? We had this big long list, right? 1 through 12, and then a couple of fractions. Do we check something from that list? I don't want you to yet, because we have not ruled out the possibility that negative 2 is another root. Just because it worked once doesn't mean it won't work again. It might. So let's go ahead and do negative 2, and then if that doesn't work, we can move on. So we have 4 times 2 is negative 8. Add them up, negative 3. There we go. See, this is another root. I kind of knew that was going to happen. But you don't. Sometimes you may see double roots. These are called multiplicities. So in this case, we've got a multiplicity of, looks like, at least 2. We'll see where this factoring goes. We still have that x plus 2, right, this guy up here. And we found another x plus 2. And now we take these and make those our new factored term right here, which is 4x minus 3. And all of a sudden, this thing is fully factored. Okay, remember, if you're at the point where you have only two terms left, a degree of 2, you stop synthetic division. But I just did it here to show you how it works when you're searching for multiple roots. And at this point, it's all factored. Now, what was this question asking for in the beginning? Oh, we want the actual roots. Okay, so the actual roots of this are, well, negative 2. Okay, let me circle these in blue. Negative 2 is one of our rational roots, and negative 2 is another rational root. So do we enter it twice? No, it's just negative 2. And what's the last rational root? Well, it is going to be 3/4. Okay, from that last factor right there. Now, if you had, what is going on? Give me my pen. If you had, for some reason, I don't know, maybe you've got an appetite for pain or something. If you had started at the end over here with your fractions, you might have found 3/4 as one of the actual roots, and then negative 2 at the end. It's not really important what order you find the roots in. But using these roots, we can now write this in fully factored form. This is x plus 2 squared times, what was that again? It was 4x minus 3. 4x minus 3. So that is how you factor high degree polynomials.